Hello everyone. Continuing with our previous discussion on quantization process, we had come across a error which I have told you it is a quantization error, and this quantization error is popularly known as quantization noise, which is the topic of our today's discussion. So the use of quantization introduces an error defined as the difference between the input signal M and the output signal V. Correct? Here we have seen right here. So this is the quantization error, and the error is called as quantization noise. Here you can see in this waveform the difference between quantized signal and the actual message signal is shown. Here instead of using discrete amplitude levels, they have shown the signal with sample and hold output. That is quantized signal only, but it is in the staircase form. This is actual quantization. Okay, here the difference between quantized voltage levels and the actual signal is shown. So that is plotted over here. As you can see, the difference between actual sample values and the quantized signal. So the error whatever you are seeing here is known as quantization noise. So we need to understand this quantization noise, and for that we'll derive an expression in terms of signal to noise ratio. If signal to noise ratio is high, then we can say the effect of noise is less because of the quantizer. If signal to noise ratio is low, then the quantization noise is high and we cannot reproduce our signal at the receiver. For simplicity, let the quantizer input M be the sample value of a zero mean random variable capital M. A quantizer G maps the input random variable M of continuous amplitude into a discrete random variable V. So M is our input where continuous amplitudes are there, whereas V is our output with discrete amplitude levels. So M and V are considered to be random because amplitude levels whatever we get are random in nature. Okay, so now the quantization error can be defined as we already know, M minus V. It might be small m minus v or capital M minus V. Both are equally acceptable. With input amplitude levels having zero mean and quantizer assumed to be symmetric, the quantizer output will also have zero mean, and thereby quantizer error Q will also have zero mean. And then in order to find the output signal to noise ratio, we need to find the mean square value of the quantization error, or you can say the variance of the quantization error. Now for that, consider an input M of continuous amplitude in the range minus maximum to plus maxima, that is say minus 5 volt to plus 5 volt. That is the range in which signal is varying. Assuming a uniform quantizer of the mid-rise type, we find the step size of the quantizer given by delta is equal to 2 into M max by L. What is delta? Delta is step size, whereas M is maximum. The difference between positive maxima and negative maxima is 2 times the maxima, right? That's what is written. L is the total number of representation levels. For a uniform quantizer, the quantization error Q will be having sample values bounded by minus delta by 2 to plus delta by 2. It is because we know that the maximum error what we can get is plus or minus delta by 2. So if delta is sufficiently small and L is sufficiently large, it is reasonable to assume that quantization error Q is a uniform distributed random variable. And then the probability density function of the quantization error can be given by the equation 7.37, where fq of q is equal to 1 by delta in the range minus delta by 2 to plus delta by 2 for q. Otherwise, the PDF or probability density function will be 0. Using this, we can write the variance of the quantization error as following equation given by 7.38. Okay, here sigma suffix q square is integration from minus delta by 2 to plus delta by 2 q square fq of q into dq. That is the standard equation, where if you substitute for fq of q between minus delta by 2 to plus delta by 2 as 1 by delta and simplify the equation, you will get delta square by 12 as given by the 7.39 equation. And here, what is L? L is the kth representation level, as you know from this equation here. K is equal to 1 to up to L. L is the representation level of kth amplitude value. And we are going to relate it to number of bits to be represented in the next level of our digitization of signals. So for that, let R denote the number of bits per sample used in the construction of binary code. So what is this? This we have already seen in the previous example here. Since we had four levels, we have represented each level by 2 bits. 2 to the power 2, we can get 4 different levels. 0 0 for one level, 0 1 for another, 1 0 for another, and 1 1. Likewise, R is the number of bits which we are going to use to represent each voltage level. That's why L is given by 2 to the power R. So what we can understand from this is, based on number of bits from which a sample we can represent, we have to decide number of levels. If we have a digital circuitry which can generate only 3 bits, then 2 to the power 3, which is 8, you can represent a signal by only 8 levels. If you have a sufficiently large digital circuitry where you can generate 4 bits, 5 bits, 6 bits, then 2 to the power 5, 2 to the power 6, 2 to the power 4, that many number of levels you can have in the quantizer. Okay, so that is L is equal to 2 to the power R. Now that can be rewritten as R is equal to log L to the base 2. Now substituting this equation, that is 7.40 and 7.36, where we had 2 into m max by L, it will be 2 into m max by 2 to the power R. Now using this delta value in the previous equation of variance, we are going to get variance as 1 by 3 m max square into 2 to the power minus 2R. Now this is the variance is nothing but noise power. So using this, signal to noise ratio at the output can be given as P divided by sigma Q square. So this will be 3P by m max square into 2 to the power 2R. That is our signal to noise ratio. And from this, what you can observe here, you can observe that as the R value increases, signal to noise ratio increases exponentially. So number of bits, if you use more and more, the signal to noise ratio increases, or the quantization error becomes minimum as the number of bits increase. That means you can have many samples to represent. So it will be a close approximation of the actual signal. Now considering a full load sinusoidal modulation. Sinusoidal modulation means the input signal power, if we consider a sinusoidal signal, then P is equal to AM square by 2 is the power of the signal, and the range of quantizer will be between minus AM to plus AM. So using that in the previous equation of noise, we will get the quantization noise as sigma square is equal to 1 by 3 AM square into 2 to the power minus 2R. Substituting that value, signal to noise ratio at the output we are going to get as 3 by 2 into 2 to the power 2R. Expressing signal to noise ratio in decibels, we will get SNR at the output as 1.8 plus 6R, where R is the number of bits we are going to use to represent each voltage level. Now, for various values of L and R, we have a signal to noise ratio table. You can see if we have 5 number of bits per sample, then we can have 32 different levels, and signal to noise ratio is 31.8. Similarly, if we can represent using 6 bits, then we'll have to have 64 different levels. Similarly, 128 levels can be represented by 7 bits, 256 different levels can be represented by 8 bits, and the corresponding signal to noise ratio output, you can see here that as we go on increasing the number of bits, signal to noise ratio is increasing, and when we increase bits from 5 to 8, then the improvement in the signal to noise ratio is by around 17 decibels. That's all about the quantization noise. In the next session, we'll try to understand pulse code modulation, that is PCM.